In this video, I'm going to talk about open circuit test or no load test of a transformer. So open circuit test is also called OC test. So this OC test, the main reason to do this test is to find out the internal resistance, core resistance and core reactance of the transformer. Okay, that's the main advantage of doing the OC test. By using OC test, we can find these parameters. So how can we find that? I will explain that in this video. So in the first diagram, you can see a transformer. Whenever we connect supply V1, since this secondary is open, that's the reason we call this as open circuit. Since the secondary is open, I'm just connecting a voltmeter here to measure the voltage. We know that voltmeter resistance is infinite, internal resistance is infinite, so it's not short circuited, it's just open circuited. Okay, now whenever I connect the source here, whenever I connect a source here, there shouldn't be any current passing through this because it's a secondary is open, but in reality there is always some current passing through it to create the magnetic field. At the same time, there are losses in the core. That losses are going to be covered by using the no load current. So for sure we will see some amperage. That amperage is nothing but no load current. Okay, that is indicated by I naught. Okay, now whenever we do OC test, we always do it on the LV side, not on the HV side. The reason behind it is, when we say LV is nothing but low voltage side. So if you look at the previous example, I have 2300 by 230 volt, right? So we always, the open circuit test, we always do it on the LV side. The first advantage is it's low voltage. Probably it is available in the labs, and getting 2300 volts might be little difficult. You can use another transformer, a step up transformer to do that, but you need to have the another transformer to step it up or step it down. Now that's one advantage. Another advantage is, whenever you see this here, say if this is a 230 kVA transformer, kilovolt ampere, can you guys tell me what is the primary current? Now the primary current is 100 ampere and secondary current is 1000 ampere. So whenever I give 230 volts, the maximum current it can see is 1000 ampere. Huge amount of current at full load. I'm talking about full load. Anyway, we're doing OC test, open circuit tests. Now if I connect, on the primary side, I can see only 100 amperes. Now if I do this test on the HV side, this ammeter reading is going to be very small, so it's hard to read. See, for example, if this ammeter is reading 10 amperes on the secondary side, on the low voltage side, it will read only 1 ampere on the high voltage side. Okay, so that is the reason we always connect OC test on the low voltage winding. By using OC test, we can find out RC and XM. So while doing OC test, this is a wattmeter. Wattmeter will give you power. Okay, so whatever that wattmeter reading is nothing but the iron losses. Why not copper losses? There is a small amount of copper loss because the I naught current is passing through R1 too. So there will be a small amount of copper loss, but this I naught is very small compared to the I1. Okay, when we connect it to the load, I1 is the current passing through this. So when we compare to the I1, I naught is very small. So the power losses are nothing but I square times R. So I naught square times R1 is very small compared to I1 square times R1. So that is the reason I'm neglecting the copper losses there. Okay, so wattmeter reading will give you copper losses, and cos theta naught will give you the power factor. and I can find V1 and I can find I naught. Okay. Now the currents flowing here, we call it as IW, and the current flowing here is I mu. So now this wattmeter reading is nothing but iron losses, which will give you V1 I naught times cos theta naught. Okay, but when you are, we're going to do this experiment in our lab. In the lab, you can you can measure these quantities, all 4 quantities in the lab. But our goal is we need to find this RC and XM. Okay, now the current IW is nothing but I naught times sine theta naught. Okay, I'm sorry, that's cos theta naught. I naught times cos theta naught, or I mu equal to I naught times sine theta naught. I already know what is cos theta naught. If not, we can find P equal to V1 I naught times cos theta naught. From here, I can find cos theta naught. Cos theta naught equal to P over V1 times I naught. P is nothing but the wattmeter reading. This is one way to find. Once I have IW and I naught, IW and I mu, RC must be V1 over IW, and XM must be V1 over I mu. This is how we'll find RC and XM. This is one way. Another way is, since it is parallel combination, by the way, I'm assuming this value is negligible. That is the reason I'm not considering any voltage drop across that. Okay, as I mentioned, this this I naught is very small, so the voltage drop here is very small, negligible compared to the voltage drop there. So if you are supplying 230 volts, probably 228 229 volts is going to appear here, 1 or 2 volts is going to appear there. So that's the reason I'm ignoring that. Okay, another way of finding RC and XM, I can say Y. Since it's in parallel combination, Y is called admittance. Admittance is nothing but 1 over impedance. Okay, so impedance, I can say V over I naught, right? Same way, I can write Y equal to I naught over V. So Y is opposite to the impedance. This is in Simon. Okay, now I have Y. I need to find that RC and XM. So Y equal to Z plus or minus JP, where Z is the conductance. This is called conductance and this is called susceptance. Okay, both of them are in Simon. Same as we have Z equal to R plus or minus JX. So Z is nothing but 1 over R, X is nothing but 1 over B, or B equal to 1 over X. Now the wattmeter reading, P equal to wattmeter reading I square times R naught, right? So instead of R, we will do it as I square over Z. Okay, so I know this value, so this is I naught square. From there I can find 1 over Z. Once we have Z, I know, from here I found the Y, and from here I found the Z. It's just like Z square equal to R square plus X square. Same way, Y square equal to G square plus B square. Okay, now I have Y and Z. From there I can find B. Once I have Z value and B value, once I know Z and B, I can find R and X by using this. Since it's in parallel, it's look like we're doing it in a weird way, but since it's in parallel, instead of impedance, we are doing it in admittance way. Or simply, if you remember, IW equal to I naught cos theta naught and I mu equal to I naught sin theta naught. Now I can find RC and XM, which is V1 over IW, V1 over I mu. This is the OC test. So by using OC test, we can find out RC and XM. Now the next one is SC test. SC test is also called short circuit test. Now the short circuit test is also called full load test. Okay, so full load means we have to apply a full load, but most of the cases instead of supplying full load, we will do it short circuit test. The reason behind it is, say for example, if it is a simple example, I'm going to take 230 kVA and 2300 volt by 230 volt. So if this is the case, we have to have 230 kVA if you want to use the full load test. So most of the cases will not have that much load, so we'll do it by using short circuit test. So short circuit test, always do it on the HV side. That means short circuit the LV side. Most of the cases we will short circuit it. We connect it by an ammeter. We know that ammeter has zero internal resistance, so it's a kind of act like a short circuit. It will give us the copper losses. The main advantage of this SC test is it will give us the copper losses, and we can find the equivalent impedance, which is Z01 or Z02. Okay, now the important thing is never ever apply high voltage 2300 volts here. So when we look at the transformer ratio, how much current is it can handle? So this can handle around 100 ampere, right? And this can handle up to 1000 ampere. Okay, so what we're going to do, instead of supplying 2300 here, we will supply a variable power supply and slowly increase the voltage up to when we see 1000 amperes there. Okay, so probably to reach 1000 amperes, I don't think even you need to reach 230 volts. Within probably 0 to I'm just giving a hypothetical number, I'm not sure how much this is going to be. So within 10% you will reach that 1000 ampere on the secondary side. So when it is reading 1000 ampere, for sure it will read 100 ampere. Okay, so we're going to do this test on the HV side, but at the same time never ever supply the full voltage. We're going to slowly increase the voltage up to when we see the secondary current, the maximum load current. So here the maximum load current is 1000 amperes with this rating. So we will apply to that current. Since you can see huge amount of current is passing through the circuit, so if this is the circuit here, the huge amount of current is passing through it, 1000 ampere. Okay, so the current is going to pass through it is 1000 amperes, but at the same time the voltage we're supplying only 10% of the actual value. Okay, it's like 2300 volt, but we're supplying less than 200 volts, so these losses we can neglect it. Okay, that's the reason when we do the short circuit test, we can neglect the losses, the iron losses. When we're doing open circuit test, we can neglect the copper losses because those are small percentage. Okay, so I'll stop this video here. In the next video, I'm going to start solving an example. Thank you.